Hi everyone, it's Anna here, your tech nerd, and today we're gonna unravel the tangled web of threads. If you've seen the diagrams of thread management before and thought, what the heck is going on here? Then you're exactly where you need to be because we are going to make sense of it all. In this video, we'll explore how threads operate within the virtual address space, physical address space, and the process control block. We'll see how threads share and interact with the spaces when they create it, and how this impacts their functionality. Ready to explore the theory and take a closer look to some diagrams? Grab your virtual coffee and let's dive into today's tech adventure. It's going to be a thread-tastic ride. In a single threaded process, it's like having just one mechanic assembling the entire car. It's slow and meticulous. But with multiple threads, it's like having a team of workers, each specializing in different tasks, making the whole process much faster and more efficient. As we covered in the video about processes, each process comes with its own virtual address space. Let's add it right here on the user space side. Each process comes with its own stack, heap, BSS data, and text sections. When a process is created, it gets its own process control block, or PCB for short, and it's assigned on the kernel side, which includes a unique PID number, state, program counter, register, memory management section, accounting, and I/O details. Look at this diagram. Here we have a single process and it got a main thread. That's the star of the show. Let's say we have an array with numbers 1, 2, 3, 4, and 5. We'll stash this array in the stack of our main thread. Our main thread will handle the task of printing this array. In C++, we'll use the cout to do this job, which will ultimately trigger a write system call, okay? Cout is a global object of type IOStream, sitting in a global static memory within the data segment. When we use cout, it sends a write system call to the kernel. This call then displays our numbers 1, 2, 3, 4, 5, one after another. It's like the kernel is saying, here's your numbers in this order. You ask for them. No mixing up, no funny business. The main thread handles every element one by one, executing all the code inside the main function by itself. When you run a process with just this one main thread, it's considered single-threaded. Alright, let's spice things up by creating a first thread within this process. Now, instead of having just our main thread running the show, we'll introduce a helper thread into the mix. So we'll have our trusty main thread handling the main tasks and our shiny new helper thread taking care of some additional work. So it's like adding an extra pair of hands to our lone worker scenario, allowing us to tackle multiple tasks simultaneously and boost our productivity. Now we can call our processes multi-threaded. As we can see, threads operate within the same virtual address space as the process they belong to. This is because they share some of the process's resources, but they execute independently. When a thread is created, it receives its own TID number or a thread ID, state, stack, registers, and the program counter. However, threads within the same process share certain resources, including the heap, BSS, text, and the data sections. Additionally, they collaborate in managing tasks like accounting, I/O, and memory management. Since we've rolled out a new thread, we can now park a thread object on the stack of our main thread, okay? Our goal is to have this new worker thread handle the task of printing our array. So this means our worker thread will keep the pointer, size, and the number of threads on its own stack. Think of it as its personal cheat sheet. But here's the twist. Cout is a global champ launching in a shared data segment because it's in a shared space. Any thread can access it without a hitch. So when you tell the worker thread to handle the printing, it taps into Cout and makes that right system call to display the array of values, one after another. Oh, and there you have it. The output will look exactly the same, whether it's the main thread or our single worker thread doing the heavy lifting. Curious about what happens when we add one more thread? Oh, that's easy. Just clone our previous thread like it's a copy-paste operation. Here's a diagram for the visual learners. Notice how both threads share the same PID because, they all part of the same process, but they have a unique TID numbers. So let's just pretend that thread 0 has a TID of 2001 and thread 1 has a TID of 2002. They might be twins, but they're definitely not identical. So how does this new thread help us print our array? With our updated function, both threads now have access to this array. Each thread will compete to print the numbers from the array and access the shared section where our print statements are located. It's like having two workers fighting for the same set of numbers, each contributing to the final output. So after participating in our little number race, can you see how the elements can be printed in different orders depending on your system's behavior and how the scheduler allocates CPU time between the threads? The order isn't fixed and can vary with each execution. Well, we only had 5 numbers here to print, which isn't hard on the CPU, but imagine trying to handle hundreds or thousands of tasks all at once. Threads can come in handy here, right? Now here's the juicy part. How many threads can you add to your process? 2, 3, 4, 1,000? Well, that depends on a few things. Your system maximum number of threads is influenced by a factor like the operating system, the CPU, and the system resources. On the modern systems, you can typically add thousands of threads, but don't get too excited, there are limits. For instance, Linux systems might support up to 32,000 threads per process, but running that many could turn a CPU into circus act, juggling tasks like a pro. It's all about balancing performance and resourcing limits. So, while you could theoretically create an army of threads, remember, even the best CPU have their limits, and nobody wants to deal with a thread meltdown, right? There are other real cool perks that come with multithreading. See these memory areas that threads share? Well, there are some real benefits to this setup. Unlike processes, threads don't have the illusion of having their own private memory space. They know they share in the same memory address space, which means they all tap into the same global variables, heap memory, and data segments. Let's enhance our diagram by adding a page table and a physical address space. The page table acts as a translator, converting virtual addresses from our virtual address space on the left to physical addresses in the physical address space on the right. Remember, all threads within a process share the same virtual address space. So if our heap ranges from, let's say, 600 to 1100 in the virtual address space, and virtual address 1000 maps to physical address 9 for one thread, it will map to the same physical address 9 for all threads in a process. Now you might be wondering, how on earth do we map different stacks to the same physical address space? Oh, don't you worry, it's simpler than it looks. Imagine the process virtual address space is set up with a range from 300 to 600 reserved for the stack. When we create multiple threads, each thread is allocated a distinct portion of this range. For instance, thread 0 might use the stack region from virtual address 400 to 500, and thread 1 might use the stack region from virtual address 500 to 600. So do you see how each thread stack operates within its designated portion of the shared virtual address space? But the mapping to the physical memory remains uniform. This shared memory setup makes communications between threads a breeze since they don't need the complex inter-process communications. It's like they having a fun team dinner chatting about their work rather than sending a formal emails to another department in a different building. Emails that might get left on read and never replied to. Plus, threads are lighter on resources compared to processes. By sharing memory and other resources, they're not just more efficient, they save you from a lot of overhead. So, while they're busy sharing the space, they are also helping you keep things lean and mean. Here's a caveat. Just like you wouldn't let a bunch of toddlers loose in a candy store without supervision, you can't just let threads access shared memory without a bit of control. When multiple threads start messing with the same data, you're inviting the chaos. Think race conditions and inconsistent states just waiting to ruin your day. So to keep things from turning into a complete mess, you'll need to use proper synchronization mechanisms like mutex, semaphores, or signals. They are your not so glamorous but essential tools to keep everything in line and avoid a data disaster. But don't worry about syncing just yet. We'll save the juicy topic for another video. We've already covered a lot today. If you enjoyed this thread tasking journey, hit that like button, subscribe for more tech adventures, and drop a comment about what threads you're curious about next. Until next time, keep threading on and stay tech savvy. And here, your tech fairy signing off. See you in the next video. Bye!